functions are so big, they have other limits than just the ones at the two ends. For example, what would this mean? Instead of x approaches infinity or negative infinity, now we see something like x approaches 3. But that's perhaps an easier idea than approaching infinity, because we had to explain that it has to be large and overgrow any number we can think of. X approaches 3 is much more clear. Just get closer and closer and closer to 3. And as that happens, what happens with this function value? What happens to the value of this expression? So our first idea would be, well, as x approaches 3, well, what about x at 3? So if you substitute 3 into this, we get 2 times 9, that's 18, minus 3 is 15, plus 5 is 20. So is it true that if x gets really, really close to 3, then this expression's value gets really, really close to 20? I think our instinct probably says that, yes, this should be true. And it is. Now, if we wanted to sort of sniff around this problem, get the idea of what numbers can we use, say with our calculator, to find values. What does a number look like if it's really, really close to 3? It could be something like 3.1 or 3.0001, that's really, really close, or 2.9 or 2.95 or 2.99. So we could substitute these numbers and we will find that the closer we are to 3, the value indeed will be closer to 20. For example, 3.1 is quite a crude approximation compared to 3.001. We can substitute these values. So what happens when we put in 3.1? For 3.1, we get 21.12. And now we're going to do 3.0001. Very, very close. We get 20.0011. And so on. But it is really, really much, much closer to 20 than the value with 3.1. By the way, to substitute numbers like this is never a legitimate way of computing limits. This is just, again, how to get the idea, which is very different from how we verify things. Okay, so here is the problem. As x approaches infinity, men that take a walk on the right side of the x-axis and walk really, really far beyond billions and billions, right? But it was all just moved to the right. There is just one way to approach plus infinity, and that is moving to the right from its left, so to speak, right? Negative infinity can only be approached from its right-hand side by moving to the left. Now, 3 is not like that, right? 3 can be approached in many, many ways, but at least we can approach it from above or from below. And sometimes that distinction matters a great deal. For example, let's look at our good old friend. F of x equals 1 over x. We now know that as x approaches infinity, 1 over x approaches 0. As x approaches negative infinity, 1 over x also approaches 0. And if we pick x equals 2, if we put 2 into 1 over x, we get 1/2. So our instinct is that probably the closer we are to 2, the function values are going to be very close to half, right? Because on the function's graph, this is the point 2, 1/2. What about the limit at x equals 0? That's where things get really interesting. So when x equals 0, you will see that there are two very different tendencies, right? Starting at 0, if we move to the right-hand side, the function is way above, and the closer we get to 0 from that direction, the higher it gets. But on the other side, so for there, we're going to say the following. The limit of 1 over x as x approaches 0, and then this looks like a little exponent. But the way I remember it is from which infinity's direction. So 0 with a little exponent looking plus means that 0 approached from where plus infinity lives. So it's from the right. If we approach 0 from the right-hand side, and we get closer and closer to 0, that's like numbers like 0.1, 0.05, 0.00001. If we do that to the x values, what happened to the y values? Is there a tendency? And the answer is yes, it's infinity. This is called a one-sided limit or a right-side limit, right? Because this is what's happening on the right of 0. What about this other question, limit of 1 over x as x approaches 0 from the left-hand side? So if we approach 0 from its left, That means x takes values like minus 0.1, minus 0.05, minus 0.00001, and so on. What is the tendency of the y values on the graph? And the answer is that is negative infinity. These two are called one-sided limits. And this one is the right-hand side limit, and this one is the left-hand side limit. Okay, so what do we mean when we see this question? This is really three questions. Question number 1, is there a left-hand side limit? Yes or no? Question number 2, is there a right-hand side limit? Yes or no? And question number 3, are the two equal? And only if you have a yes, 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 that's when we can say that there is a two-sided limit. In this case, it's a yes, yes, no, right? Yes, there is a left side limit. Yes, there is a right side limit, but no, they are not equal. So there is no two-sided limit in this case. If we go back to our previous example, to this one, that's a two-sided limit. Because, and you can check that with the calculator, it doesn't matter whether you punch in 2.9, 2.99, 2.99999, or 3.0001, you're going to be really close to 20. Maybe, just maybe, one set of numbers would produce slightly above 20, the other one slightly below 20. That we could check out. What happens if we put 2.9 into this, right? When we put in 3.1, we got beyond. So maybe if we put in 2.9, we're going to get less. Well, let's see. If we substitute 2.9, we get 18.92, right? So we're below. Now, this may not be such a surprise because what we're observing is probably, well, this is a quadratic, so we have a parabola. So say this is 3. So when we're below 3, the y values will be below 20. And when we're above 3 on the x-axis, then on the y values are going to be above 20. That's just because the function, if you read it left to right, it increases at that interval. But that's not always the case. Functions can behave quite temperamentally. Okay, so let's go back to our idea of two-sided limit. So let's see a few examples. Unlike with limits at infinity, limits at a finite number that we're going to call two-sided limits are easier to approach. We can just substitute it into the expression. So what would be the limit of 3x minus 1 as x approaches 5? So let's first substitute 5 into the expression. We get 14. So is it reasonable to expect that this would be a two-sided limit, that is 14? So if we graph this, we will see that at 5 the function value is 14, but the question is what happens nearby? What happens when x is not quite 5 but very close to it? Would the y be close to 14? And I think just from the visual, we have an instinct that the answer is yes, this is a two-sided limit. The closer x gets to 5, the closer y gets to 14. And it doesn't matter whether we are approaching 5 through numbers slightly larger than 5 or smaller than 5. There is a slight difference, but it's not in where they're going. It's just from which way are they approaching, but they are approaching the same thing, which is why this two-sided limit exists, which means there is a left limit, there is a right limit, and they are equal, therefore there is a two-sided limit. Okay, let's see another example. This one is kind of a dangerous one. You have to be careful because our first instinct is to substitute. 6 minus 6 is 0, square root of 0 is 0. So it looks like we have a nice limit of 0. However, that's not the case. If we graph this radical would start at x equals 6, right? Which means that if we put in numbers like 5.9, 5.99, 5.999, there is no function. So because we are approaching a number that is a boundary point of the domain, we have to be careful. The left-hand side limit does not exist. It's undefined. Why? Because the limit as x approaches 6 and the little plus positioned as if it was an exponent indicates that we're going to approach x equals 6 from the right. That means we're thinking of numbers like 6.5, 6.1, 6.01, 6.00001. Those are all fine because they're greater than 6, and after the subtraction, a positive number square root exists. But what about something like 5.9? 5.9 minus 6 is negative 0.1. That doesn't have square roots, so that's not in the domain. So when we approach 6 from its left, which means we're approaching it through numbers like 5.9, 5.99, 5.999, as long as it's smaller than 6, then this subtraction will produce a negative difference, and the square root of a negative number does not exist among the real numbers. No function, no limit, right? If you look at this, this is a fine right-hand side limit, but the left-hand side limit doesn't exist, so we say undefined. So remember, for a two-sided limit, you have to have three yeses. Does the right side limit exist? Does the left side limit exist? Are they the same? This is an example where you substituted and the substitution itself did not give you a red flag, so you have to be careful. It's a little bit like crossing the street, so look to the left and look to the right, even if a nice number came out. Okay, let's see another example. So this is a really interesting example. This is a 0 over 0 indeterminate. I didn't emphasize this, but it is very important that as x approaches 0 means x is really close to 0 but not 0. So a limit basically does not discuss at, only near. So when we say here limit as x approaches 0, it is actually important that, okay, approach it but don't get there. So x is a non-zero number no matter what. Let's just figure out what the graph of this function is. If we substitute positive numbers into this expression, so forget the limit, let's just look at this example. Let's substitute 5 into it. The absolute value of 5 is 5. 5 over 5 is 1. So we get 1. What about 10? Absolute value of 10 is 10. 10 over 10, 1. It looks like anytime we put in a positive number, we just get 1. What do we get when we put in negative 5 and negative 10? The absolute value of negative 5 is 5 divided by the number itself, which is negative 5. Now we get negative 1. Same thing with negative 10, right? The numerator is plus 10, the denominator is negative 10, so we get negative 1. We're going to prove this. What happens is that, first of all, this function is badly undefined at x equals 0. But for every positive number, it's constant 1, and for every negative number, it's constant negative 1. Now let's prove this. If x is greater than 0, then the absolute value of x is just x. Then, for positive values, absolute value of x over x is just x over x, and that's 1. And if x is less than 0, then the absolute value of x is the opposite of x. And the absolute value of x divided by x is going to be now the opposite of x divided by x, which is negative 1. And by the way, this is how we're going to handle things with absolute value. We're just going to separate it when it's the same thing and when it's the opposite. Something like that is also called piecewise defined function, because we can define this piece as constant negative 1 and this piece as constant positive 1. Okay, so now let's discuss the two-sided limit of this function. As x approaches 0 from the right hand side, as we get closer and closer to 0 but don't get there, as long as we're not there, we have a constant 1. The limit of the constant function is just that number. So the right hand side limit is 1. Meanwhile, the left hand side limit is negative 1. So the two-sided limit is undefined. So we have seen already in case of 1 over x that the left limit and the right limit disagreed, but I wanted you to see a finite case. See, these are the left limit and the right limit separately exist, are finite, but not the same. Okay, let's see what's next. If there is no little plus or minus sign, that means they're asking really the two-sided limits, which is 3 questions. Is there a left limit? Is there a right limit? Are they the same? If you substitute 3 into x, we see that we are dealing with a 0 over 0 type of an indeterminate, which means that we're going to perform algebraic transformations until we bring this to a form which is no longer an indeterminate, and then we're going to substitute 3 into it again. This one is kind of an easy situation because this is not simplified. Maybe simplifying it will just do the trick, and actually I believe it will. And we're just going to work on the fact that this is a complex fraction with 3 fraction bars. Let's just reduce it to 1 fraction bar. First, in the numerator, we bring the 2 to the common denominator, which is 3x. And then we have x, because x over 3x is 1/3 minus 3, and we divide that by x minus 3. Okay. To divide is to multiply by the reciprocal, so we're going to have x minus 3 over 3x multiplied by 1 over x minus 3. You see there is cancellation here. we're gonna see another list of properties that govern two-sided limits, so limits at a number. And you will see that the properties are very similar. So the question is, what allowed us to make this step? And the answer is, this is where the replacement rule works. Because these two functions are the same except for at x equals 3. At x equals 3, this is fine. At x equals 3, this is undefined. So the two functions differ from each other just at one point, x equals 3. X equals 3, this is 1 over 6, this is undefined. So therefore, by the replacement rule, the limit of f is the same as the limit of g. And so now that we cancelled out the stuff that was making things, we sort of cancelled out the 0 over 0, right? And what's left is, for sure not an indeterminate because the top is 1. Now if we put x equals 3 into that, we get 1 over 9. And that's an interesting limit so far because that's not something that we would have guessed just looking at the question. So our intuition would not have taken us to the answer. Before we move on, is there a two-sided limit? So let's just look at the left and at the right. So what would happen if x would be slightly greater than 3 or slightly less than 3? Would there be an issue? And the answer is no. The only thing we need to worry about is exactly 0. So this one is a two-sided limit. Okay, let's see another one. Okay, let's see this one. So it's kind of cute. If we substitute x equals 2, we get a 0 over 0 type of an indeterminate. And that means first we're going to have to work on that. And because we see radicals and the expression containing the radical is complicated enough to have a conjugate, I would say let's try the conjugate first. So that means that we're going to multiply this expression by 1, where 1 is a fraction with the same numerator and denominator, and that same thing is the conjugate of the numerator. So in the denominator, we're just going to indicate the multiplication. The x minus 2 is getting multiplied by 5 plus square root of 23 plus x. Now, in the numerator, we have the difference of squares theorem, 25 minus 23 plus x. Right, the square of 5 and the square root of 23 plus x. There is cancellation, it's just that they are opposites. So I'm going to factor out negative 1 from the numerator. Limit as x approaches 2 of negative 1 times x minus 2 over x minus 2 times 5 plus square root of 23 plus x. So we factor out negative 1 and then we get the limit as x approaches 2 of negative 1 times x minus 2 divided by x minus 2 times 5 plus square root of 23 plus x. And then we can cancel out x minus 2. Now let me stop just for a second and remind ourselves that x is really, really close to 2, but not 2, which is why this step is allowed. So then what we're left with is this limit, where negative 1 divided by 5 plus square root of 23 plus x as x approaches 2. Now we can put x equals 2 into this, and we would get negative 1 over 10, right? Because if x is really close to 2, then 23 plus x is really close to 25, square root of that is really close to 5, and 5 plus 5 is 10. So basically this says that if the closer x gets to 2, the closer y will get to negative 1 over 10. And this is again sort of an interesting limit because we wouldn't guess that number just by looking at the question itself. Now, negative 1 over 10 is a two-sided limit provided that the function exists at both sides. Indeed, this is a two-sided limit because we are near 25, right? If x is near 2, we are near 25. So it doesn't matter whether we are slightly below 25 or slightly above 25. The function in both cases is defined. It doesn't matter a great deal whether under the radical we are close to 0 from one side or the other. There it does matter because we are dealing with the endpoint of the domain. Now we're in an interior point of the domain, so this is a two-sided limit indeed. Okay, let's see what's next. The limit of tangent x as x approaches pi over 2. This is going to be very similar to what 1 over x is doing at 0, because at pi over 2, tangent is not defined. Tangent is sine over cosine, right? And the problem at pi over 2, if x is near pi over 2, sine x is near 1, but cosine x is near 0, and you can do that from negative or from positive side. And when that happens in the denominator, we get something like this. So this is just before pi over 2, sort of like 89.5 degrees. If that's the case, sine is near 1, cosine is tiny positive, right? And therefore what we see is very much like what 1 over x does at 0 through positive numbers. Now, if we are a little bit after 90 degrees, say 91 or 90.5 degrees, then see the sine is still near 1, but cosine is now a small negative number, so we come back from here. And so if you ignore the rest, you just focus on this part. See, this is like 1 over x at 0. This is how something nice changes sign, but it's in the denominator. And this all happens, among other places, at pi over 2. So that means that there is a left limit is infinity. From the right, then cosine x is a small negative value, therefore tangent x is going to approach negative infinity. So the two one-sided limits exist, but they disagree, therefore the two-sided limit does not exist. The limit of tangent x as x approaches pi over 2 is undefined. Okay, here is another cute little indeterminate. If x is really, if we substitute 2 into the expression, we get 4 over 4 divided by 2 minus 2, so that's a 0 over 0 type of an indeterminate. However, if we have a rational expression that is a 0 over 0 indeterminate, remember that polynomials don't produce a 0 out of the blue. They are all brought to us by linear factors. In other words, if you have a 0, there is a linear factor explaining that 0 in case of every polynomial. I'm going to switch from 2 to 3. So if p is a polynomial and p of 3 is 0, then x minus 3 is a factor of p. So if you have an indeterminate that is a type of 0 over 0 and you're dealing with a rational function, the first thought should be factor, factor, maybe there is cancellation, and then maybe after that it's not an indeterminate anymore, which is exactly what happens. We factored x squared minus 4 via the difference of squares theorem, then we had a common factor. Now remember that x is not 2, but it is really, really close. And the closer x gets to 2, the closer this sum will get to 4. So we get 4 for the limit. Is it a two-sided limit? If you look at the expression, there is no radical, there is no logarithm, so a negative number is no trouble, it's just division by 0. If you wanted to graph this thing, if x is not 2, we have x plus 2, and we have undefined if x is 2, right? So how do we graph that? Well, it is x plus 2, and 1, 2, this point should be 2, 4, and this is the point that we're going to take out. So this is a two-sided limit. Okay, so here is another example. What is wrong here is that we have seen that the limit of tangent x as x approaches pi over 2 does not exist, because one side is infinity, the other side limit is negative infinity, even though it appears in a form that it is squared. So we can say that there is a two-sided limit of infinity, but still 1 minus infinity squared and 1 plus infinity squared, that's an infinity over infinity type of an indeterminate, so we are not allowed to make conclusions from these facts alone. What we have to do instead is to perform algebraic transformations until it is in the form that is no longer an indeterminate. And in this particular case, we're going to need a little bit of trigonometry. Now, if we multiply both upstairs and downstairs by cosine squared x, that would clear the denominator. So then we're going to get cosine squared x minus sine squared x divided by cosine squared x plus sine squared x. Now the denominator is now 1 and the numerator is cosine of 2x. And this is no longer an indeterminate. We are talking about the limit as x approaches pi over 2. We are talking about the limit of cosine of 2x as x approaches pi over 2. Well, as x approaches pi over 2, 2x approaches pi, and cosine pi is the first coordinate of this point, that's negative 1. In case of trigonometry indeterminants, we have lots of trigonometric identities to use to transform it into a more convenient form. if c is not 0, then c over 0 is not an indeterminate. So let's say that c is a number, say 5. Let's see if we can concoct something like this. So c is 5 over x minus 8 as x approaches 8. Now what's going on here? So 0 over 0 is an indeterminate, but not 5 over 0. If the numerator is really, really close to 5 and the denominator is really, really close to 0, sort of close to 5, close to 0, what can we then say? It is sort of 5 times 1 over 0, 5 times very close to 1 divided by very close to 0. That's like 1 over x at 0, or 5 over x, right? If the denominator approaches 0, but not the numerator, then the answer is that the answer can be 3 things: infinity, negative infinity, or no limit, because it's kind of both. So for example, in this particular case, now you know from college algebra that this is like 1 over x shifted to the right by 8 units and then stretched by a multiplication, right? So it's a relative of 1 over x. It's just this vertical asymptote is that x equals 8, and we have a multiplication, right? And then you can see that one side is negative infinity, the other side is positive infinity. You can have a two-sided limit. For example, the limit as x approaches 8 of 5 over x minus 8 squared. That's going to be good for plus infinity, because now, no matter which side we're on, if the number is really close to 8, then x minus 8 is really close to 0, and now after squaring, it's still close to 0, but now it's positive. So this one is going to act like this around its vertical asymptote. Thank you for watching.